So, here we now take a break from Verilog and look at some of the so called VLSI design styles. Well, when you talk about VLSI design styles, it means some of this I already talked about in the last lectures, like I talked about ASIC, application specific IC, I talked about FPGA. There is something called semi custom and full custom designs. There is something called gate array which falls between FPGA and ASICs. So, we will see some of the features of these design styles. The reason I would be discussing this is that some of you may be actually designing this kind of circuits. So, you may want to see a correlation between the Verilog coding and the design that you will be doing and your final target hardware. So, there are a few differences. So, unless you understand these differences very clearly, it will be a little difficult for you to customize or modify your design as you move from one design style to another. So, we start with our discussion on VLSI design styles. Now, VLSI design cycle, already I mentioned a little bit earlier that the VLSI design complexity has increased immensely over the years. Manual design or synthesis is simply out of the question. Now, you have to use computer aided design tools, which means automation. So, there are many reasons for doing this: time to market computation, cost, optimization and so on. Talking about the VLSI design cycle, here I am showing you a slightly more detailed stepwise breakup. So, starting from the system specification, you can go to functional design, which is the register transfer level design, logic design, gates, flip flops, circuit design in terms of transistors, physical design. Physical design is something which we will again look at a little more. Design verification, that whether our design is correct, finally fabrication, and after fabrication packaging the chip, testing and debugging. These are the overall steps in the VLSI design cycle. Now, talking about physical design, which is somewhere here. So, after your circuit netlist is done, we go for physical design before you can actually go for fabrication, right. So, physical design roughly says that I start with some kind of a netlist, typically at the gate level or the transistor level, and from the netlist I ultimately translate it into my manufactured hardware. So, my manufactured hardware can be ASIC, it can be FPGA, it can be anything, but the step is like this: I start with a netlist at a sufficiently lower level, gate level or transistor level, and I map it into my hardware. Okay. Now, in this steps of physical design, we again may have to go through a number of intermediate steps. Like there are steps called partitioning, floor planning and placement. Like you have to decide, if it is a large design, how to break it up into smaller partitions, and on the surface of silicon where to place them, how to plan my total chip floor plan and so on. Then comes a very important step of routing. So, how to interconnect these blocks that I have already placed. Static timing analysis, extremely important in the modern day context. So, after I have completed placement and routing, I need to check that whether my design is meeting my timing constraints or not. If not, I may have to go back and change these things. Signal integrity, crosstalk analysis, these are related to timing analysis, these are also very important. And when everything is fine, I see that everything is meeting the requirements, then I complete my physical verification process and do a step called sign off. Sign off means I am satisfied with my physical design. Now, I can proceed to fabrication. Okay. Fine. Now, talking of the design styles, well, I shall be looking briefly into these 4 design styles. There is the first category of programmable devices. I will talk about field programmable gate array FPGA and also simple gate arrays. Then for standard cell design or semi custom design and full custom design. The last 2, they fall under the category of ASICs, application specific IC. Fine. Now, which design style to use? This is a matter of deciding on part of the designer. There is a trade-off. There is a trade-off between hardware cost, performance and the total time required for the design. You see, FPGA is the easiest to design, but the circuit delay maybe is bad, but ASIC performance is very good, but hardware cost and time required will be very high. Okay. So, these parameters are often very conflicting. So, when we are going for a particular kind of design, we have to look into the bigger context, that exactly for whom we are designing it, who are the potential customers and what are the main objectives that need to be satisfied. So, in that way we can decide on the optimizing criteria in a much better and concise way. Fine. So, we start with FPGA, field programmable gate array. Now, FPGA, as I mentioned earlier, this offers user programmability or field programmability, means we can do the programming in our lab, sitting on a table, sitting in front of a table, you can do it. Now, what an FPGA is really? FPGA, as I said it is a programmable device, but inside there is an array of logic cells. Well, array means many thousands of logic cells. They are placed in a regular array and they are interconnected via routing channels. Now, both these logic cells and the routing channels are programmable, means their functionality can be modified. Now, in addition to it, there are some other cells called IO cells. Now, these logic cells can be either IO cells or they can be something called lookup table blocks. And these routing channels, interconnections, they are manufactured in different way, either using static RAM or using something called anti-fuse. Static RAM means inside there are small memories. From outside I can store some bit pattern in those memories, zeros and ones. So, if I store a 0, some switch will be open, if I store a 1, some switch will be closed. So, in that way I can program my interconnection. Now, anti-fuse is something which is a little different, it is one time. So, by passing a high current between 2 points, so either I can blow out or I can connect a connection. Now, anti-fuse means normally there is no connection. So, if a high current is flowing, then the material will be fusing, it will be melting and a connection will be established. So, there are some FPGA manufacturers which also use this kind of anti-fuse technology. Fine. So, means obviously FPGAs are very easy to use. These chips are manufactured by a number of vendors like Xilinx, Altera, Actel. Their products vary widely in capability. There are FPGA chips now available which are very fast, very complex, radiation hardened. So, you can map very complex and large designs into those FPGA chips as well. Okay. And development boards and CAD software are available. Now, here we have a very quick look at a particular FPGA architecture, Xilinx XC4000. You see, this is a bird's eye view of the whole chip. You see, at the periphery there are some small rectangles, these are the so called IO blocks. or IO cells. These IO blocks contain some multiplexers, flip flops, tri-state buffers. You see, from external pins there are signals which can be coming in or going out. Some of these blocks can be input pin, some of these blocks can be output pin. So, by programming these blocks you can configure them. Okay. Then you have these rectangular blocks in between. These are something called configurable logic blocks. So, again by programming this you can make them work in various ways. So, actually we shall see a little later. So, how we can do this, and in between the configurable logic blocks there are some spaces where some programmable interconnects are there. By again programming these switches here, I can make connection from one block to the other as per my requirement. So, whatever design I have, I can map them on to this fabric and I can program them in such a way that appropriate functionality and appropriate interconnections are made. So, that whatever circuit I want to design, I want to implement, that gets implemented on the FPGA chip. Okay. This is the basic function. So, the configurable logic block, it looks like this. You see, I am not going into detail, but the more interesting thing is that there are two blocks here. There are two blocks here which are called lookup tables. So, as you can see, there are 4 inputs and 1 output. These lookup tables can realize any 4 variable function. So, I will just explain a little later how. And there is also 2 flip flops in the output. So, by properly selecting these multiplexers, there are many multiplexers you can see. So, you can actually connect them in a variety of ways, right. So, you can program them. So, CLB, as I said, there are 2 4 input function generators here, these 2. They are implemented using lookup table using 16/1 RAM. So, how it is done? Let us try to explain. Suppose I have a 16:1 memory RAM. There are 16 words, each containing 1 bit. So, there will be 4 address lines and there will be 1 data output or input, whatever you say. So, in this memory location there will be 16 locations. You consider a 4 variable function a, b, c, d. So, any 4 variable function, if you look at the truth table, there will be 16 columns. Suppose I want to realize some function f of 4 variables. I construct the truth table and I just fill up these memory locations by the output column of the truth table. So, once I do this, my function is ready. So, I apply a input, that corresponding location will be selected and that corresponding output will be generated. So, just by modifying this memory, I can implement any arbitrary function of 4 variables. This is how the programmability comes into the CLBs, right. So, in addition to implementing 4 input functions, it can also be used as a memory if you require 16/1 memory. And also inside you have seen that there are 2 flip flops, there are two 1 bit registers, they can be configured as a flip flop or a latch. Clock polarity, you can have leading edge triggered, falling edge triggered, set reset, all these facilities are there. The lookup table, as I had mentioned, one lookup table is shown here. I am showing one lookup table, flip flop, multiplexer. So, this lookup table can implement any function of 4 variables which gives its power, as I had said. Okay. So, just one small example. So, if you are given a function, we create the truth table of the function just as I said, load the output column of the truth table into the SRAM. So my function is ready. So, I apply ABCD to the input, I get F as the output of the memory. So, any 4 variable function can be realized. Now, mapping, there can be area delay trade-off, like means I am just showing an example. Suppose these are some gates and these are the inputs, lines are inputs. This is a given net list. So, I want to map them into those lookup tables. So, one way of mapping may be like this, this can be 1, this can be 1, this can be why. You see, if I take this part of it, this whole thing, there are total 4 inputs, you see 1, 2, 3 and 4. So, overall this is a 4 input and 1 output circuit, this part. Similarly, this whole thing is 1, 2, 3, 4 and 1 output. So, any sub circuit with any number of gates with maximum up to 4 inputs and 1 output can be mapped to LUT. And here whatever remains I can map into one more LUT. So, here there is only 2 inputs. Okay. So, there are 3 LUTs which are required here. Delay is 2, this is 1 level of delay, 2 level of delay. Now, you think of an alternate mapping. Let us say I take this as 1, let us say I take this as 1, there is also 4 inputs, 1 output, and I take this as 1, 1, 2, 3 input and 1 output, and this as 1. So, here there will be 4 LUTs, delay will be 3 because this will be 1 delay, this output is coming here, this will be another delay and then this 3. So, this is a bad mapping, this is a better mapping, right. So, this LUT mapping is a big problem, this is a challenge. So, the IO cells are also quite complex, as you can see, the IO blocks, there are also latches there are flip flops, these IO pads, there are tri-state controls, buffers, pull ups, there are a lot of things. You can again there is some RAM, SRAM inside, by loading them you can configure the output pins, that whether it is an input pin or an output pin, whether you require tri-state control and so on, whether it is a strobed output, you need clock leading edge, falling edge, all these things you can program. So, these are extremely flexible cells. So, by specifying a few bits, you can specify exactly how these individual IO blocks will work. Okay. So, and talking about the routing, see these CLBs are there inside which those LUTs are there, and in between there is some space. There are some switch matrices with some finite number of wires that are connected, and this switch matrix is also programmable. Like one wire of this can be connected to a wire here, say a wire here can be connected to a wire here, and the CLBs are connected to these wires. So, by suitably programming the switch matrix and connecting the CLBs to these, so we can make any kind of connection, say the output of this CLB can be connected to the input of this CLB. Okay. So, this is also programmable routing interconnection. So, in FPGA you say everything is programmable, the logic is programmable, logic in terms of the lookup table, interconnection is programmable in terms of the switch matrices, and also the IO blocks can be programmed, they are also programmable. So, when I say in that board I had shown earlier that I am downloading some data on the FPGA board, we are actually downloading all this programming data. Depending on my circuit net list, the synthesis software which is there, it will be generating this programming data, and if I download it on my chip, I will be getting my desired functionality on that chip. Okay, fine. So, FPGA design flow, if you just look at it, so it consists of design entry to start with, you can do it in Verilog. Then the software that is provided by the vendor, like I talked about Xilinx, IC or Vivado, they do placement and routing, partitioning, but here it is different. Here partitioning means partition into sub circuit with maximum 4 inputs and 1 output, because each partition I will be mapping to one of the LUTs, and this LUTs will be placed into one of the CLBs, configurable logic blocks. Now, if you talk about the switch matrices, you see there is a finite number of wires, right, but if you have a very bad kind of a placement, you have placed them in such a way that lot of wires need to be connected across a switch matrix, but maybe one matrix is allowing only 4 wires to be laid. So, you cannot complete the routing. See, you may have to change the placement and again try the routing. So, FPGA placement and routing is also a big challenge. So, if you have a good routing, if you have a good placement, then routing will be easy. If your placement is not good, maybe during routing it will fail, you may have to move some blocks around, again try, and ultimately you will be getting some solution. So, this placement and routing, bit stream generation is that programming. So, whatever you want to program, ultimately it is generated in the form of a stream of bits, and these software they allow you to analyze the timing behavior, layout, that within the layout which part is heavily utilized, which part is not utilized. Of course, you can also do simulation and check whether functionally it is correct or not. Then finally, you can do the download, you can directly map it to the Xilinx hardware device. Like just talking about that FPGA board that I showed you earlier again. So, here I told that there is a port here, some pins through which you connect a cable to the PC, and you can download that bitmap file here to the FPGA board, and this FPGA chip will be automatically configured in that way, right. Okay. So, with this we come to the end of this lecture, and the next lecture we shall be looking at the other design styles, namely gate array, semi custom and the full custom design styles. Thank you.